Okay, we said last time that we would start today by calculating the concentration for each absorbance value, and where am I going to go to figure out the relationship between concentration and absorbance? All right, Y here represents absorbance, so I'm going to change this to A, and then X represents concentration, so I'll change that to C. So I can solve for C. Concentration is going to equal absorbance divided by 7.26 or so. So then we can just do that calculation for each of the absorbance values from the experiment. So what do I get? David? 0.085, 0.070, 0.056, 0.047, 0.039, 0.032. All right. So if I want the rate over the first minute, remember here's my reaction. 2A plus B makes C plus D. I'm measuring the concentration of B. So the rate of the reaction as written, since B has a coefficient of 1, is just going to be the rate of disappearance of B. So it's going to be negative 1 over 1 times delta concentration of B, delta T, which over that first minute is 0.085 minus 0.070, or the other way around. Change in time over the first minute is 1 minute. Units on the top are mole per liter. So I'm going to get the rate in moles per liter per minute. So it looks like 0.015 moles per liter minute. Then you go ahead, take a second, calculate the rate over the fifth minute, the average rate, and I'll write it up here. So we were asked for three things. We were asked for the rate over the first minute, the rate over the fifth minute, and then the average rate over the whole 5 minutes. All right, so I did the calculations, and don't feel the need to necessarily copy down all the math, because it's really just some subtraction and division. Now, why did I ask you to do this? I want you to notice something about the reaction. What happened to the reaction rate over the course of the reaction? It decreased. The reaction rate slows down. So when we talk about reaction rate, the interval that we're looking at matters. We can't just say, oh, this reaction has a rate of such and such. Well, we have to say, well, over this interval, the reaction had a rate of such and such. Because we see that it started out faster at 0.015 moles per liter minute and ended up slower, 0.007 moles per liter minute. We'll talk about why that's the case in a little bit. Actually, we can get at it right now. Why do you think the reaction slows down? This is pretty common. Most reactions slow down over the course of time. All right. There's less reactants around, right? Reactants get used up. So they're actually reacting less frequently over time. We'll get into the details of that a little later. But this is pretty common for a reaction rate to start out higher, end up lower. A lot of you saw it in the lab. You drop your calcium carbonate in the hydrochloric acid, and it starts fizzing really fast. And you look 5 minutes later, and maybe there's just a little bit of bubbling going on. So you use up the reaction. You use up reactants. The reaction gets slower. When we want to talk about reaction rate, it's important that we specify reaction rate over what time period. We also sometimes will talk about the instantaneous reaction rate. What do you think instantaneous reaction rate means? At one specific moment, what is the rate of the reaction? Now, if I have a graph, a lot of times we represent our data graphically. If I have a graph, how could you find the rate at a given instant? The slope, yeah. Julia brought up the word derivative, which we'll come back to in a little bit. I am a little later going to relate this to calculus. Not that you need to know calculus to do what you need to do for this class. But whenever we're dealing with rates of things, a lot of times it is going to be related to calculus in a way. And so for those who are taking calculus, I'll try and make that connection for you. But if I want to find the rate initially of this reaction, and I have a graph of concentration versus time, the simplest thing for me to do would be to draw a tangent line to the graph. So if I have this graph, I want to know what's the initial rate. I would start by drawing a line tangent as best I can. Yeah, that was that. All right. So that's more or less a tangent at the beginning of the graph. So if I want the initial rate, I would calculate the slope of this line, right? Remember the rate of this reaction is going to be negative change in concentration of A over change in time, but there's something else I need to include. Going back to yesterday, I need to consider the coefficient here. It's actually 1 over 2 delta A, delta T. And I can just use my tangent line. Now, what 2 points would be convenient points for me to use for my tangent line to calculate slope? The intercepts, yeah. So I have change in concentration of A between the intercepts would be negative 0.25 molar. And change in time between the intercepts, about 45 seconds. Actually, I'm going to make my life easier. I'm going to put this into minutes. So this would be 0.75 minutes. That makes it easier because now I don't need a calculator. I can say this is going to be equal to 0.25 over 1.5 molar per minute. So that's going to be equal to 0.166, 1/6. The question is, would we have to say mole of reaction per minute? Probably. You know, these units here, maybe it would be better to write mole reaction per liter per minute. I think the standard is if it's not indicated otherwise, then it's in moles of reaction per liter per minute. All right. So that's just measuring reaction rates. What questions do you have about measuring reaction rates? All right, then, going back and just checking in on the outline. All right, how do we define and measure reaction rates? We're done with that. We're going to move on to how do we change a reaction rate? What are the things that will make a reaction rate change? So to do this, we're really going to visualize reactions. How do reactions occur? What do reactions occur between? Well, there's a hint on the slide. Reactions occur between atoms and molecules. So think about a reaction between atoms and molecules. What's really going on during a chemical reaction? All right, so bonds break and new bonds get made. So how does that actually happen? All right, the two things that are reacting have to be close to each other. They actually have to collide. So for a reaction to happen, we need the reactant particles to collide. Two substances can't react if they're across the room from each other. Okay. Does that mean every time two reactant particles collide, there's going to be a reaction? No. Okay. Why not? What other requirements are there? John? All right. They have to have enough energy to start breaking their bonds. We're going to give a word to that. We call it the activation energy. So, number one, with enough energy to start breaking the old bonds. Or sometimes it might be two things that are going to form a bond, but they have to overcome a little bit of repulsion from their electron clouds on the outside. So they have to collide with enough energy to start breaking the old bonds and maybe overcome a little repulsion. Between electron clouds. They don't actually need enough energy to fully break their old bonds. In some reactions, the old bond needs to fully break before the new ones form, but in most cases, it's kind of happening simultaneously, and so they don't have to fully break the old bond before the reaction gets going. So they have to collide with enough energy to start breaking old bonds. And there's another one. For this one, I like to use a pretty simple analogy. Let's say a reaction between two people is like, I'm going to hand someone this pen. Who would like to demonstrate with me? All right. Stand up. And if you're at home, I'll try and narrate. All right. So Max and I are going to undergo a reaction where we exchange a pen. Okay. So let's demonstrate the reaction. We're just walking along, and we bump into each other, and I hand him the pen. And we walk away. All right, that's pretty simple. Now let's try it again. Ready? Now I'm going to approach him backwards with the pen in front of me. Okay, we just collided. Did we exchange the pen? No, why not? Because my back was toward him. The reaction was happening with my hand, so if I collide with him with my back, we can't do the reaction. Same thing is true of molecules. When they collide, they have to have the right orientation to start breaking and forming the bonds that need to break and form. Thank you, Max. So the idea is that the particles need to collide, but it turns out in a given reaction mixture, only a small fraction of collisions are actually going to successfully lead to reaction. Most collisions, the two reactant particles just bump off each other. That's kind of important that most collisions are actually unsuccessful. Because, for instance, in this room, there's lots of oxygen. There are also lots of flammable things in the room. Oxygen is bouncing off of those flammable things all the time, and yet the room is not on fire. Why? Because it turns out most of the time when oxygen bumps off those flammable objects in the room, it doesn't have enough energy to get the reaction going. It doesn't have enough energy to overcome what we call the energy barrier, the activation energy for the reaction. And so, activation energy is keeping us all from being on fire right now. So the question is, can you supply the energy to overcome activation energy through doing work instead of through heating things? And the answer is definitely yes. So, for instance, this is how I believe older engines work, where the energy for ignition of the fuel is not from a spark plug; it's from the actual compression in the cylinder. So you compress the gas enough that gives it enough energy to overcome the activation energy, and that's what causes the explosion that then pushes back. Nowadays, most engines, the ignition is from a spark plug, but that definitely is possible that work can supply the energy. Yep. All right, so we are going to get into the math later. Right now, we're going to write an equation kind of from a simple perspective, and that simple perspective is going to be that reaction rate will be equal to the frequency with which the molecules collide times their success rate, times the percentage of collisions that are actually successful. So to say that more simply, it's going to be the collision rate times the success rate. So from a conceptual standpoint, what are the two ways that I could increase the rate of reaction? Okay, you're getting more specific. So, so some people said increase the temperature. We'll get to that. But in thinking in terms of this abstract equation, Stephen, we could increase the collision rate, so make them collide more frequently, or increase the success rate, so increase the chances that each collision is successful. So now to take that to specific ways that we can increase reaction rate. When we have a reaction involving a solid, we saw this in the lab. What's a way to increase the collision rate between a solid and other reactants? Increase the surface area. Yeah. So for solids, increase the surface area. That will increase the collision rate. So I'm going to code these by, here, I'll put it up here. CR means increase the collision rate. Oh yeah, sorry, I had it at the top of the slide already. Make particles collide more frequently. So we can increase the surface area, which will increase the collision rate. If we have a mixture of a solid and a liquid, what's one thing we did? I know there was a group in here who did it. Stirring or shaking, agitating. Causing the surface area to be more exposed to the liquid. You're going to make them collide more frequently. If we have gases or dissolved things, increase the pressure, but for dissolved things, it's not pressure. Concentration, we can increase the concentration. Which for a gas would result in increased partial pressure of the gas. And then the one people already mentioned, to make them collide more frequently, make them move faster, so increase the temperature. Because if they're moving faster, that means they're colliding more frequently. Rough. So the question is, when we did the exchange of the pen, we collided in the wrong orientation and nothing happened. So could you design a solid where the surface, the reactive part of the solid is actually pointed inward so that it won't ever react because it never collides in the right orientation, but if you break up the solid, now it can? Absolutely. So, for instance, stainless steel. Stainless steel has a coating on the surface. I believe it might be chromium. It's some other element that is not likely to get oxidized. But down below, you have more just exposed iron atoms, and so if you scratch up the surface, now it can start to rust. So there definitely are things that have some sort of thing on the surface, and you get down below that surface, and now it'll react. All right, so then ways to increase the success rate. Well, one way to increase the success rate we just mentioned. Temperature. Why would increasing the temperature increase the success rate? Okay, so the claim was, since they're moving faster, they're going to collide more frequently. Yes, so that it won't. But student tried to relate that to orientation. It actually doesn't increase the percentage of collisions that are in the right orientation. It does increase the frequency of collisions, which means it does increase the frequency of collisions in the right orientation, but not the percentage that are in the right orientation. It actually addresses the other part. They have to collide with enough energy to start breaking the old bonds. The more kinetic energy they have when they collide, the more likely that they will overcome that energy barrier. So so the question is, does stirring and mixing actually change the orientation? Stirring and mixing change the orientation of particles, sure, in a random way. It's not going to increase the percentage of collisions that are in the right orientation. Right? If you think about it, we're talking about atoms and molecules which are really tiny. The only thing that could increase the percentage of collisions in the right orientation is something else that's also really tiny. Something that might be able to put two molecules in a bear hug and say, hey, you two, you're perfect for each other. I see a lot of hands in the air from former biology students. All right, why don't you say it in unison? Enzymes. So enzymes are molecules that essentially can find two reactants and hold them in just the right orientation. It's like a matchmaker that grabs the two and like pushes them together and says, you two, you're perfect for each other. Sit closer together. So enzymes are an example of, this broader category of compounds that we call catalysts. So catalysts really operate in two different ways that are both related to lowering the activation energy of the reaction. It lowers the activation energy, so even at the same temperature, more of the collisions will be able to overcome it. But it also can, in the case of enzymes, actually address the orientation issue and make the two molecules more likely to have the right orientation, because it really just has this little site that attracts one and a little site that attracts the other, and then it kind of folds them together. So yeah, a catalyst lowers the activation energy, which means the colliding particles are more likely to have enough energy. And in some cases, like enzymes, it actually holds the two molecules in the right orientation. So we have a number of ways to increase the collision rate. We have a couple of ways that we can increase the success rate. What questions do you have at this point? All right, so let's tie this to what we've seen before. Remember, we introduced this Maxwell-Boltzmann distribution way back in at the beginning of the year. We've returned to it a couple times. We're returning back to it again. Remember what this describes. So this is showing us what is the kinetic energy, or what percentage of the particles have a given kinetic energy in a sample. And so in a given sample, some particles are moving faster than others. And we get this distribution where there's always some particles over on the right-hand side that have a lot of kinetic energy, with the average being somewhere back. Here I've shown at low temperature, there's a lot more particles with low kinetic energy. At high temperature, there's more particles with high kinetic energy, which makes sense. So with this distribution, we can think about, okay, if there's a certain energy that particles need to overcome this activation energy barrier, the graph can show us like what percentage of the particles will be successful when they collide. So first of all, if I pick a certain activation energy, let's say it's right here. Then in my low temperature sample, essentially only these particles over here will be successful when they collide. Whereas for that same reaction at high temperature, keeping the activation energy in the same spot, what happens to my success rate at high temperature? Increases dramatically, because now it's all these particles over here that are going to be successful at high temperature. So just saying the same thing we said a minute ago in graphical form. On the next slide, we'll do the same thing, but we'll keep the same temperature and imagine we're changing the activation energy. So now if I take the same distribution and I have a given activation energy, for an uncatalyzed reaction, and I think about, what about if I lower that activation energy? And actually, I don't know why I didn't do this earlier. Activation energy, we abbreviate as EA. Yes, and the room just erupted with EA Sports. It's in the game because, marketing is so hard to escape. And when I grew up playing those games, and I still think of it every time I write EA. You can't escape it. And if you don't know what I'm talking about, then good. Then you never wasted a bunch of time with video games. So with a catalyst, I'd have a much lower activation energy. And again, we can see, without the catalyst, we might have just these particles over here on the tail end of the distribution that have enough energy that would be successful. But then with the catalyst, suddenly there's a much greater percentage of collisions that are going to be successful. So all this would be successful collisions with the catalyst. All right, so we have these different ways that we can affect the rate of a reaction. Some of them increase the collision rate. Some of them increase the success rate. So good, we're moving along. So next we get into actually visualizing what's going on during a reaction. And I think I'll start with just the energy diagrams today. So this is the abstraction. This is us thinking about what's actually going on in terms of potential energy over the course of the reaction. We call these reaction coordinate diagrams. So a reaction coordinate diagram essentially is a graph where on the x-axis we're putting reaction progress, which is sort of this somewhat nebulous term to say, like, how far along in the reaction are we? So on the left-hand side is like when you just have the reactant particles completely separate. On the right-hand side is when you just have the products completely formed. And the middle is as the reactants are changing into the products. Okay? So in a reaction coordinate diagram, we have on the left reactants. And on the right, we have products. And this whole middle space is where, you know, they're changing into the products. And there's always a big hill in the middle to get over. Well, it's not always big. There's always a hill in the middle to get over. Sometimes it's smaller, sometimes it's bigger. We give a name to the peak of that hill. We call this the transition state. So the transition state is the highest energy point along the reaction pathway. At the transition state, the old bonds are partially broken, the new bonds are partially formed. So in the next slide, I'll actually like draw kind of a fake generic reaction. So imagine we have a reaction between a molecule. Let's see, I want to make this consistent with what I'm doing later. All right. So I have a reaction A plus BC makes AB plus C. All right, this is my reaction that I want to look at. And let's say it's represented by this pathway. Then over here on the left, I would have A and I would have B bonded to C. So over here, I would have A and B bonded to C, completely separate. Maybe I'll draw them. Hold on a second. I'll draw them a little farther apart. Oops. Now, as the reaction starts occurring, I'm going to start breaking the BC bond and I'm going to start forming the AB bond. So when I get to the transition state, I'm going to have this thing where A is somewhat bonded to B and B is still somewhat bonded to C. You know, and maybe as we're climbing this hill, it's like A is getting closer, but it's still farther apart. We go through the transition state. The transition state is essentially the point of no return. It's like you got to the top of the roller coaster. Now you got to slide down. So as you slide down the other side, what's going to happen is A and B are going to get closer and C is going to get farther away. So as we go down this side, you'll have A closer to B and then C getting farther away. And when you get to the products over here, now you have A, B, and then C is separate. So that's what these graphs represent. They represent what's happening in terms of potential energy as the old bonds get broken and the new bonds get formed. Now, what information can we get out of a reaction coordinate diagram? All right, one thing we can tell is whether a reaction's endothermic. This is why I gave you 3 of these, because I thought it would be crowded to write all this stuff on one. So now, the next one, we can tell whether it's endothermic or exothermic. This reaction here, would we say is endo or exothermic? Endo, because what happened to potential energy? It went up. All right, so this is going to be change in energy. And I'm not necessarily being clear on what I mean by energy here. Later in the year, we'll distinguish between what we call enthalpy and Gibbs free energy, and I don't want to go there right now. But what this tells me is this is an endothermic reaction, okay, because delta E is positive. All right. There's another piece of information I can get. Activation energy. Where's the activation energy? It's the difference between where we started and the peak. So the activation energy is how high is that mountain that we have to climb. And we can use this to visualize the energy changes that occur during a reaction. And you can actually think of the reactants as being like little marbles that have a certain amount of kinetic energy. And they start rolling up the hill. Now, if you start rolling a marble up this hill and it doesn't have enough kinetic energy to get over the top of the hill, what's going to happen? It goes back down. Is that a successful or unsuccessful collision? Unsuccessful. So you have lots of collisions where maybe you start to form the new bond a little bit and start to break the old bond a little bit, but it doesn't quite have enough energy to get to the top, and it just falls back down, so the particles bounce off each other. Okay? But sometimes you have enough energy to get up over the hill, and so those marbles make it over. That would be a successful collision. Okay? I included this next graph just to show an example of an exothermic reaction. Here, change in energy is negative. But we could measure the activation energy here as well. The other way that the marble visualization is helpful is that if you imagine rolling a marble up this hill and down the other side, when it gets to the other side, is it going to be moving faster or slower than it did at the beginning? It's going to be moving faster because it has come down a bigger hill than it went up. Whereas in the first reaction, if you rolled a marble up the hill and it had enough energy to get over the hill, when it gets to the other side and rolls down, it's going to be going more slowly than it was before. So it's endothermic, so the temperature is going to go down. All right? So those diagrams are hugely important to us just as a way to visualize what's happening in terms of energy. So the question is, can you calculate the speed of the reaction through the slope? The answer is definitely no. These diagrams aren't necessarily built on real, the x-axis isn't really built on real numbers necessarily, because we're talking about reaction progress. You know, in reality, there are some computer programs you can use to simulate reactions in 3 dimensions. And you get these, you know, obviously a graph this simple can't represent what's going on in 3 dimensions, but you get sort of energy saddle points and you know, it's much more complicated than we're displaying here. So we will use these really only in a qualitative way. The only quantitative information that's really contained would be the vertical stuff. So delta E, right, the change in energy, that's something we can measure, and activation energy is something that can be measured. but as far as the x-axis goes, it's not necessarily measurable. But consider that qualitative. Yeah, good question. Other questions about reaction coordinate diagrams? All right. Well, I am so pumped up about this. I hope you guys are enjoying it. So we will pick this up again tomorrow, but we'll pick this up again on Monday. I mean, but we have now gotten through energy diagrams. We've got to talk about reaction mechanisms and catalysis. I can't wait to talk about catalysis because we get to tell nice soap opera stories.